Hello and welcome back to the video lectures on replacement model. So let us continue our discussion on second model or the replacement of items that fail suddenly with the example. We have already seen the brief introduction to this model in the previous video. So let us solve an example based on this model.
So this is the data. Following mortality rates have been observed for a certain type of light bulbs in an installation of 1000 bulbs. So there is an installation of 1000 bulbs and this is the historical data available on how they fail. At the end of week 1, 9% of 1000 bulbs are likely to fail. At the end of second week, 25% of 1000 bulbs are likely to fail. By the end of fourth week, 85% of 1000 bulbs are likely to fail, and by the end of sixth week, 100% or all the bulbs are likely to fail. Okay. Using this data, we can also find out how many bulbs are likely to fail between subsequent weeks. Okay, so these probabilities are cumulative. So okay, so cumulative means they go on adding up. So 0.09. So 25%, for example, is including week 1 and week 2. Okay, similarly, 85% by the end of fourth week includes all the first 4 weeks. Okay, and hence, exactly by the end of 6 weeks, all bulbs are likely to fail. Using this data, we can also find out how many bulbs are likely to fail between week 1 and week 2 by simply subtracting 0.09 from 0.25, which will be 0.16. So 16% of the bulbs, 16% of 1000 bulbs are likely to fail between week 1 and week 2. Similarly, between week 2 and week 3, 24% of 1000 bulbs are likely to fail, and you can do similar calculations between week 3 and week 4, between week 4 and week 5, and week 5 and week 6. So this is the given data on the costs. Rupees 3 is the cost of replacement of single bulb when it is replaced individually, and the same bulb costs 70 paise if it is replaced in group. That means if all 1000 bulbs are replaced, then the cost of replacement of single bulb is 70 paise. Okay, so that means 0.7 is C1 and 3 is C2. And company wants to come up with an optimal interval of group replacement, or the company wants to know after how many weeks all the bulbs must be replaced with, of course, the individual bulbs replaced as and when they fail. Okay, and company wants to come up with the time interval t, maybe every week or every 2 weeks, every 3 weeks, that we are going to find out depending upon the condition that we know. So company wants to come up with a replacement policy that that gives us this interval of small t, also that gives us the minimum cost of replacement. So this is the condition that we have to find out the optimal interval of replacement that results into the minimum cost. And we have already seen this equation. We also seen what is the meaning of this numerator here. Now, to find out this, to compute this inequality, or the left hand and right hand sides of this inequality, we need to find out this C of t. C2 is already known, but we need to find out NT. We need to find out how many bulbs are likely to fail individually, and then uh, N is capital N is all bulbs, so which we know are 1000. We already know C1, we already know C2, but we need to find out this bracket, which gives us the number of individual failures that are likely to occur at the end of every week. Okay, so let us find that. Okay, so let us calculate the expected number of failures. And remember that when we are calculating expected number of failures at the end of each week, we are going to consider both group failure as well as individual failure. And this is the data from the previous slide, which gives us the probability of failure at the end of each week. And this is the data about the probabilities of failure between the subsequent weeks. So this, for example, uh, this is the probability uh, of failure at the end of first week. Similarly, this is the probability of failure between week 1 and week 2. So 16% of the bulbs are likely to fail between week 1 and week 2. Similarly, 24% of the bulbs are likely to fail between week 2 and week 3. 36% of the 1000 bulbs are likely to fail between week 3 and week 4. 12% of the bulbs are likely to fail between week 4 and week 5, and 3% of 1000 bulbs are likely to fail between week 5 and week 6. And if you calculate P7, it will be 0 because all of this sum to 1. So the probability of any bulb fails between week 6 and week 7 is 0, between week 7 and week 8 is 0, and you can go on with this. Okay. So let me erase this. So let us start computing. We want to calculate the expected number of failures, group plus individual, at the end of each week. So by the end of week 1, we know that 9% of 1000 bulbs are likely to fail. And hence, if you want to find out how many bulbs are likely to fail, you must multiply 1000 by the probability 0.09, which gives us 90. So that means 90 bulbs are likely to fail at the end of week 1. Similarly, by the end of week 2, 16% of the bulbs are likely to fail. That means 1000 into 0.16. So uh, these 160 bulbs are likely to fail by the end of week 2, plus 9% of these 90 bulbs are likely to fail at the end of week 2 because they would have completed week 1 week of their life. Okay, so 9% of those 90 bulbs are likely to fail. 90% of those replaced bulbs are, sorry, 9% of those 90 bulbs are likely to fail by the end of week 2, and this figure comes out to be 168. Similarly, by the end of week 3, 24% of 1000 bulbs are likely to fail, and hence out of 1000 bulbs, 24% are likely to fail, plus out of this 168 bulbs, those were replaced at the end of week 2, 9% of them are likely to fail. So 168 times 0.09 plus 16% of these 90 bulbs, those were replaced by the end of week 1, are likely to fail by the end of week 3 because they have completed 2 weeks of their life, and hence 90 times 0.16. So this gives us 269. So 269 bulbs are likely to fail by the end of week 3. And similarly, if you go on doing calculations, you should get those values. By the end of week 4, 432 bulbs are likely to fail. And you can go on computing the same number by the end of week 6. By the end of week 7, that comes out to be 291. Okay. Now, based upon these expected number of failures, now we can compute the costs that are involved in the left hand side and right hand side of the condition. So let us check the condition here on this slide by using this tabular format. And in column 1, I have mentioned the week number. In the second column, I have mentioned the left hand side of the condition, C2 into NT, or the cost of individual replacement. In the third column, this is the average cost of group replacement. Okay, so let us start calculations from week 1. By the end of week 1, we know that there are 90 individual replacement possible. Hence, we know that there are 9% bulbs are likely to fail and 9% of 1000 is 90 as calculated on the previous slide. And if we replace these 90 bulbs individually, then we are going to pay 3 rupees per bulb for this, and hence cost of individual replacement by the end of week 1 is 270. Okay, so this is C2, 3 C2, and this is NT. So by the end of week 1, 90 bulbs are likely to fail. And then we calculate the group replacement cost. So by the end of week 1, we already know that 90 bulbs are likely to fail. So this will be the component in the group replacement policy. And also, if we replace all the 1000 bulbs at the end of week 1, then we will have to pay 70 paise for each bulb. So for group replacement policy, the average cost comes out to be 970 divided by 1, because this is week 1, hence 970 divided by 1 is 970. Okay, then we check the condition whether this C2NT is greater than CT by T, and this condition is not satisfied at the end of week 1 because this 270 is less than 970. So let us move on to week 2. Again, we will calculate the cost of individual replacement during week 2. So we know that as calculated on the previous slide, 90 plus 168 bulbs are likely to fail by the end of week 2, and if we choose to replace them, or if we replace them, then we need to pay 3 rupees per bulb, and this comes out to be 774. Okay, and at the end of week 2, if we uh, replace them in group, that means if we replace 1000 bulbs at the end of week 2, then we need to pay 70 paise plus 168 plus 90. So I think that comes out to be 258. Okay, so if 258 bulbs are likely to fail at the end of week 2, then we will individually replace 258 bulbs, and we need to pay rupees 3 per bulb for that, and this comes out to be 737. So this actually 1474, and CT by T, so average, as 2 weeks are completed, we need to divide this by 2, which comes out to be 737. Okay, so now again we check the condition whether C2 and T is greater than or less than equals to CT by T for week 2, and this condition is satisfied here. 774 is greater than 737. So this is the optimal policy that the uh, the group replacement should be done after every 2 weeks. So anyway, let us compute the values for week 3 also. So by the end of week 3, we know that these many number of bulbs have to be replaced individually. So uh, 527. So you can calculate it just like on the previous slide, and we need to pay 3 rupees for their individual replacement, and this comes out to be 1581. And then if we perform group replacement, then again if we replace 1000 bulbs, then we need to pay 0.7 plus 1581, and this comes out to be 2281 with group replacement policy, and average will be divided by 3 equals to 760.8. 760.33. So let us see whether the condition is satisfied for week 3. Yes, it is satisfied because 1581 is greater than 760.33.
But the average cost for group replacement at the end of week 3 is greater than that of week 2. So if we replace uh, all the items, or if we implement the group replacement policy after every 2 weeks, then we need to pay 737. However, if we replace them after every 3 weeks, we need to pay 760.33, and hence we choose to perform group replacement at the end of every 2 weeks. Okay, so you can also calculate for week 4, week 5, and so on.
So these are the same calculations on the previous slide. So finally, this is the solution, that group replacement must be done after every 2 weeks, and this will result into minimum cost. So we are done with replacement models in this video. I will soon upload the videos on 5th unit.